Now we are going to do electrical conductivity of extrinsic semiconductor. Here we consider a block of semiconductor of length L and area of cross section A. Length L and area of cross section A having electron density Ne and the hole density as Nh. Let V be the volume, V be the potential difference across applied across the ends of the semiconductor. Now make a figure. This is the positive terminal of the battery and this is the negative terminal of the battery. V is the potential difference applied across the ends of the semiconductor, and this is I, which is current, which describes the current flowing in the semiconductor. These are the electrons and these are the holes. So now the magnitude of the electric field applied is, what is the magnitude? Magnitude of electric field applied is E, that is electric field, is equals to potential difference applied across the semiconductor divided by length of the semiconductor. So we can say that E is equals to V upon L. So this is the equation 1. Due to the electric field, both electrons and holes in this semiconductor moves in a mutually opposite directions with drift velocities VE and VH. VE and VH are the drift velocities of electron and hole. So the current produced by electron and hole is in the same direction in the semiconductor. So the total current, therefore the total current, that is I, is equals to the current produced by the electron plus the current produced by the hole. So we can say that I is equals to IE plus IH. This is equation 2. Since electrons in the conduction band and holes in the valence band, electrons in conduction band and holes in valence band are moving randomly. You can see in this picture that in this figure shows that electrons and holes are moving randomly. They are not moving in a particular direction in the semiconductor. So but it shows that electrons in the conduction band and the holes in the valence band are moving randomly like electrons in metals. Okay, now the current of electron is equals to NE AeVe, like as we have done earlier, the drift velocity. So there is VE, not VD, because this is the drift velocity of electron. Okay, and this is the number of electrons and area of cross section in the electron. So IE is equals to NEAVE, and similarly IH is equals to NHAEVH. This is the drift velocity of the hole. So from equation 2, put the value of IE. What we have done, that I is equals to IE plus IH, right? So put the value of IE and IH in this equation 2. So what we get, that I is equals to NEAEVE plus NHAEVH. Got it? Now A is common in both cases, so take it common. So A common, and NEEVE plus NHEVH. E is also common, so AE and EVE plus NHVH. So this is I. So I over A, which is equals to E and EVE plus NHVH. As we know that the resistance of the semiconductor, as we know that, let us consider that R be the resistance of the semiconductor and rho is the resistivity of the semiconductor. So as we know that the resistivity of the semiconductor is equals to resistance into area of cross section over length. So this is the resistance, this is the area of cross section, and this is the length of the semiconductor. So resistivity is equals to RA upon L. Now dividing equation first, that is E is equals to V upon L, and this is equation 3, and divide equation 1 by 3. We get E over rho is equals to, what is the value of E? What is the value of E? V upon L. Equation 1, E is equals to V upon L. So put the value of E here, V upon L, and put the value of rho here, that RA upon L. So we can write it as V over L is equals to RA over L. How we can solve it? V over L into L upon RA. So L and L cancel with each other. So we get V over R is I. We get this. And V over R is I. We get I over A. Got it? And this is our equation number 4. As we also get that I over A is equals to E common NEVE plus NHVH. So we have to put the value of I over A here. So we have E over rho is equals to I over A. Put the value of I over A. We give this equation as number star. So I over A is E NEVE plus NHVH. We know that the mobility of electron is defined as the drift velocity per unit electric field. So what is the main thing is that what is mobility of electron? It is defined as the drift velocity per unit electric field. Per unit electric field. That is, mobility of electron is represented by mu E, which is equals to the drift velocity of electron divided by the electric field. Okay, so the drift velocity of electron is mu E into E, and similarly the mobility of holes. Mobility of holes. Same, mu h is equals to drift velocity of hole divided by E. So the drift velocity of hole is equals to mu h into E. So put the value of, in equation 5th, put the value of VE, put the value of VE and VH from these expressions. So we have E over rho, E over rho is equals to E and E into mu E into E plus n H into mu H into E. So E is common. E is common in both the cases, so take it common. E is cancelled with E, so 1 upon rho is equals to E and E mu E plus n H mu H. So as we know that the electrical conductivity is always reciprocal of resistivity. So what it shows that this is a electrical conductivity. So reciprocal of resistivity is equals to electrical conductivity. That is sigma. So we can write it as sigma is equals to E into n E mu E plus n H mu H. Got it? So these relations, these two relations shows that the conductivity and resistivity of a semiconductor depend upon the electrons and the hole number density. This is the electron and the hole number density. But it shows that the electrical conductivity of semiconductor depends upon the number density of electron and the number density of hole and their mobilities. These are the mobility of electron and this is the number density of electron. This is the mobility of hole and this is the number density of hole. So as number density of electron and hole increases with rise in temperature, therefore the conductivity of the semiconductor increases. As we increases the temperature, their conductivity is also increases. So with the rise in temperature, the resistivity decreases. As the temperature increases, the resistivity decreases with the rise in temperature. At room temperature, this electrical conductivity for germanium, this, when the temperature is increases, the electrical conductivity of germanium is always greater than the electrical conductivity of silicon, because the number density of the charge carriers is more in case of germanium as in case of silicon. So this shows the electrical conductivity in the case of a intrinsic semiconductor.